Microplastics are tiny plastic particles, generally defined as being smaller than 5 millimeters in diameter. They are categorized into primary and secondary microplastics. Primary microplastics are intentionally manufactured in this size range, often found in products like cosmetics and industrial abrasives. Secondary microplastics result from the breakdown of larger plastic debris due to environmental factors like UV radiation, ocean currents, and physical abrasion. Both types are prevalent in various ecosystems, including oceans, freshwater bodies, and soils, and can infiltrate food chains, potentially affecting human health. The global production of plastics has increased significantly over the past few decades. Microplastic particles have been in the marine environment since the early 1970s. Most natural polymers that were once employed in our daily lives have now been replaced by plastics due to their high longevity, inertness, and relative affordability. However, what once seemed like a blessing for the world is now becoming a curse due to the vast use of this synthetic polymer and the excessive amounts of plastic garbage it has produced. The situation is worse as their natural decomposition is more difficult, which finally causes the plastic to accumulate in almost every environment. Potential impact on human health while research is ongoing. Microplastics pose various potential health risks to humans, primarily through ingestion, inhalation, and skin contact. Ingestion, microplastics enter the human body mainly through contaminated food and water. Seafood, especially filter feeders like mussels and oysters, often contains high concentrations of microplastics. Drinking water, including bottled water, also frequently contains microplastic particles. Health effects: ingested microplastics can carry toxic chemicals and harmful microbes. Chemicals like bisphenols, phthalates, and persistent organic pollutants POPs can leach from microplastics, potentially leading to endocrine disruption, reproductive toxicity, and other health issues. Smaller microplastics or nanoplastics might penetrate gut walls, enter the bloodstream, and cause inflammation. Inhalation, microplastics, particularly from synthetic fibers and tire wear, are suspended in the air and can be inhaled. This is of particular concern in urban environments where airborne plastic particles are more common. Health effects: inhaled microplastics can accumulate in the respiratory tract, potentially leading to respiratory issues such as inflammation, oxidative stress, and even lung cancer in severe cases. The impact on lung tissue is still being studied, but occupational exposure to microplastics has already shown adverse respiratory outcomes. Skin contact: although the skin is an effective barrier, prolonged exposure to microplastics, especially those carrying toxic substances, could theoretically lead to skin irritation or absorption of chemicals in certain circumstances. Biological mechanisms and cellular impact: at a cellular level, microplastics may interfere with cellular processes. Oxidative stress: microplastics and their additives can cause oxidative stress, leading to cell damage and inflammation. Cellular entry: smaller micro and nanoplastics can cross cellular barriers, possibly leading to apoptosis or other disruptions in cellular function. Immune system response: the immune system may recognize microplastics as foreign particles, leading to chronic inflammation if exposure is prolonged or excessive. Microplastics also impact ecosystems and biodiversity. Marine organisms ingest microplastics, mistaking them for food, which can lead to malnutrition and physical harm. Additionally, microplastics can act as vectors for pollutants, concentrating toxic chemicals and transporting them through food chains. While significant progress has been made, understanding the full health implications of microplastics requires more research, particularly in long-term exposure. Studies on chronic exposure to low levels of microplastics are needed to determine long-term health effects. Establishing standard methods for measuring microplastics in different environmental and biological samples is crucial for consistent and comparable research. Regulatory action: many countries are taking steps to limit primary microplastics, such as banning microbeads in cosmetics, but broader policies are needed to address secondary microplastics from plastic waste. While a lot of focus has been placed on microplastics in aquatic media as part of research efforts, more than 4 billion people live in urban areas. Urban activities are the main hotspots of plastic pollution. where the economic framework, regulations regarding plastics, management of urban waste, environmental consciousness of inhabitants, urban topography, decoration, architectural features, and local climate can all have an impact on the discharging and distribution of microplastics in urban areas. The understanding of airborne microplastics in population centers is limited and lacks clarity and direction. There are only a few studies reporting the physicochemical characteristics of microplastics in the urban atmosphere. However, the concentration of airborne microplastics in indoor environments is far greater than outdoor places. Textiles, traffic-related sources, littering, agricultural and industrial activities, and marine microplastics are the main origins of airborne microplastics. Additionally, airborne microplastics can mostly enter the human body through inhalation route. Furthermore, airborne microplastics can serve as a vector for pathogenic agents and toxic pollutants. Wind, wet, and dry deposition, temperature, along with physical features of cities affect the abundance and behavior of airborne microplastics. It has also been demonstrated that airborne microplastics pose a significant threat to human societies. Therefore, extensive research still needs to be conducted on various aspects of microplastics.